All right, so maybe we can get started. And here's the rundown for the lesson today. There's kind of a lot of material, but we're only going to go through some of it. So there'll be a couple sets of lecture slides that you're likely to want to look through. That'll be up on the course page, but I'm not going to go over those. So for parts 2 and 3 of this kind of lecture stuff, that'll be an online only thing. And this relates to the, not only maybe to like the exercise for this week and for next week, but also for like this final project thing that we'll go over briefly when we get to talking about the exercise after the introductory lecture stuff. But before we do that, are there any questions about exercise number 5 or anything like that came up in that exercise? I guess it was a bit more straightforward than the week before. Yeah. Okay. So yeah, if there aren't any issues about that, then what we'll do is we'll move on to the topic for today, and that is to introduce you to thermochronology. I'm assuming that no one really has any previous exposure to thermochronology, but maybe you've heard the word at some point. But since I'm assuming you haven't seen this before, I'm going to kind of start with the basic stuff, and this will relate to the exercise this week, next week, and also the final project, so it's kind of useful to get some idea of what we're doing. So we're going to start just by introducing what the concept is, what is thermochronology, and then talk about something called a closure temperature, which is closely related to thermochronology, and at the end talk about how we can estimate this thing called a closure temperature, which is what the code you'll use for this week's exercise does. So to give you some idea of what I'm thinking for these last few exercises and things, we can start here with why are we even talking about thermochronology at all? Well, there's a couple reasons. One is that it's quite popular analysis type used to study tectonic and erosional processes over long time scales in places like this, mountainous areas where rocks are being eroded and slowly exhumed to the surface. So it kind of brings in a little bit of things we've already been talking about, a bit of erosion, a bit of tectonics. So it's kind of a natural thing to talk about in general as far as topics go. It's also related to heat transfer processes. We haven't really done any modeling of this kind of thing yet. You'll do that this week. But when you talk about heat transfer in the lithosphere, especially in places where you have active tectonics, you have a combination of heat being advected and heat being conducted or diffused. And these are both equations that we've seen already before. So this is kind of tying in a couple equations with the advection equation and diffusion equation that we've previously seen. The plot itself, just in case you're kind of unclear about what's here, is just predictions of temperature in the lithosphere of the Earth. So like about 130 kilometer thick layer here. And the different lines are for different assumed temperature conditions at depth. So whether we assume the temperature is at some constant value at infinite depth or at some fixed depth, or for instance, at the blue line, we just assume that there's just constant geothermal gradient at the surface. That'll change the way in which the temperature varies with depth in a model. And you'll see in the code we use today how that works. And of course, another thing that it brings in, there's some of the equations we dealt with back in lessons 1 and 2. So this kind of goodness of fit idea comes up. We won't deal with it necessarily today, but next week's exercise will involve combining what we do this week with the goodness of fit calculations that we saw earlier. So like this chi-squared statistic you can use to compare how well a prediction fits some measured age. So essentially it ties together a lot of the things we've already been dealing with in one nice kind of combination of exercises. So to get started, we have to talk a little bit about what thermochronology is in general. And perhaps you're more familiar with the idea of geochronology, which is something I think pretty much everyone gets introduced to in introductory geoscience courses. So it's the idea that we can date geological materials and the science that's sort of associated with doing that kind of dating. One of the most common ways in which we can date geological materials is to use some kind of radioactive isotope that is produced by the decay of some parent, and the accumulation of the daughter isotope allows you to measure the age if you know how frequently the decay happens. So basically, that's the kind of idea behind geochronology. The distinction between a geochronological age and a thermochronometer is sort of an important one, and it's maybe something that'll take a little bit of time to sink in. But generally speaking, when we date minerals with a geochronometer or some kind of geochronological system, say uranium decaying to lead, we're getting the absolute age of the crystal. We're getting basically the time at which that crystal was created. So that's also the interpretation that we typically have, is we look at the total amount of lead that's accumulated and we say, okay, that gives us the age of this crystal. And if we go out and do that to the bedrock here, we're going to get quite old ages, generally speaking. For a thermochronometer, we also can look at the amount of daughter isotope that accumulates in a crystal, but it doesn't necessarily give you the age at which that crystal formed. And the reason is that the daughter isotope is not trapped inside the crystal at all times, but rather whether it stays in the crystal depends on the temperature of the mineral. So what it gives you is a time since the rock was at a certain temperature in the earth, rather than an absolute age at which the crystal was created. So, and we'll see this in some diagrams here in just a second. So if we talk about the system, it's basically like a geochronometer. We have some kind of radioactive parent isotope. Often this is uranium or thorium, but it could also be potassium. We have some daughter isotope that gets produced, which could be, in the case of uranium or thorium, it might be helium that's the daughter isotope here. So rather than looking at lead, which is basically not mobile, we look at something like helium. Or if it's argon decaying, often we're looking, or sorry, potassium decaying, we're often looking at argon as the isotope. And then the mineral that is sort of host to this system. So essentially the picture looks a little bit like this. We've got some kind of spontaneous decay, and it produces a daughter isotope. Yeah.
What's the minimum age you can predict with the radioisotope?
The minimum age?
Yeah.
I would say practically speaking, minimum ages would be maybe 10 to 100,000 years. So it's, yeah, I mean, generally we're looking at things that are fairly old. In many cases, it's because like the half-life of uranium is pretty long. So in order to accumulate enough, like a measurable amount of daughter isotope, you need to have decay for a fairly long period of time, or a really high concentration of uranium or thorium to start with. And that's not that common. So, but yeah, we're looking kind of 10 to maybe 100,000 years minimum. Maximum, there really is no, I wouldn't say there's an upper bound. Practically speaking, some of the systems get complicated at really old ages, but you know, the half-life of some uranium isotopes is old enough that you could measure the age of the Earth if you have a way of trapping the daughter product for that whole time. So, but the picture looks like this. We've got decay of some mineral, and then it's inside a crystal here. And we'll talk a little bit more about the details in just a second. Actually, I don't think that this is so important. This is just kind of another definition, but thermochronometry is sort of similar word to thermochronology, but it's basically just the use of these thermochronometers, so these mineral systems, to understand the temperature history of a rock, or mineral rather. And we'll kind of come back to that later, so don't worry about that too much for right now. Just a couple definitions that, in fact, I'm just going to skip over for the moment. But the basic idea here is we want to somehow use this temperature history. It's going to be some time since the rock was at a certain temperature to tell us something about past tectonic activity or past erosional activity. And the key thing then becomes connecting this temperature with some depth in the Earth, because then you can start to say, okay, well, if this mineral says it's 10 million years since it was at 100 degrees, that's useful. But if I can figure out how deep 100 degrees was, now I can start to say how fast that mineral came up to the Earth's surface. And then you can begin to relate that to rates of erosion or tectonic activity. So this turns out not to be a very simple thing to do, to relate this temperature to a depth in the Earth. I mean, there's some ways you can do it by just assuming that temperature increases at some constant rate with depth, but that's not really often the case in places where you apply thermochronology. So there's some slides about this in I think the stuff we won't go through, but you can take my word for the moment. But the essential kind of idea, I think, is shown here in this little, I guess it's kind of meant to look something like an hourglass, where the gray balls here would be a parent isotope, and the white ones would be the daughter isotope that's produced by radioactive decay. Essentially, if we want to look at the way in which these mineral systems can operate as like end members, one is that the system is a closed system. So anytime there's a decay, that daughter isotope is trapped inside the crystal. That's like the normal way that geochronology works. You have parent isotope decay, the daughter is trapped in the crystal, and the longer it accumulates, the older the age would be, and we can sort of calculate that from the half-life of whatever the parent isotope is. The difference here in thermochronology is that we can also have this open system behavior. And what that means is that when the daughter isotope is produced, it's not trapped inside the crystal, or not necessarily trapped inside the crystal, but it may diffuse out of the crystal and be lost. And so essentially, not everything gets trapped, and so obviously the age you're going to measure then, if you only have a few or some portion of the daughter isotope, the age you measure doesn't really connect nicely to the geochronological age you might calculate with something like uranium lead. So the daughter product is basically being continuously produced. As you have decay of the parent isotope, you're more or less continually producing daughter, but you might lose some of the daughter product or daughter isotope to diffusion. Yeah.
What are the conditions under which you could still use an open system?
Well, the open system, I mean, you don't necessarily... Essentially, there's going to be some period of time for most all of these samples where they're going to experience a closed system behavior. The problem is that when it's behaving like an open system, you basically don't have any history. So if you lose the daughter isotope, you have no record that how long this crystal has existed and been producing a daughter isotope by radioactive decay. This will become maybe a bit more clear in a minute, but essentially the open system behavior is something that we're not really interested in. It's more a question like, when does it become a closed system? Yeah. And the way it works out is that the open system behavior is pretty much what happens at high temperature. So when this mineral is at a high temperature, especially with isotopes like helium, the helium can diffuse out of the crystal. And at lower temperatures, the sort of kinetics slow down and the helium is more or less trapped inside the crystal because the rate of diffusion goes down as a function of temperature. So essentially the picture looks something like this. If we're down here deep in the Earth where temperatures are relatively high, this plot's meant to show the kind of daughter concentration, so the amount of daughter product, or you could think about it like an apparent age if you want to kind of take the next step and say the daughter product that is accumulating is related to the age. But at high temperature, essentially what we see is that there's basically no accumulation of daughter product, because when a helium, like alpha particle, is produced by radioactive decay, for instance, of uranium, that alpha particle quickly diffuses out of the crystal, and you have no record that it was ever produced. If you're up here shallower in the Earth, so like close to the Earth's surface, then you generally get this closed system behavior, so that any isotope, daughter isotope that's produced, is trapped in the crystal. And so then you have a record that the more of those accumulate, you can start to then calculate what the age is. And the transition between these two, between the open system, which would be down here at the bottom, and the closed system, which would be up at the top, the transition between the two is sort of a gradual thing. It's controlled by rates of diffusion, and it's not like diffusion just shuts off when you get to slightly cooler temperatures, but it sort of gradually slows down. And as that rate of diffusion slows down, you start to trap more and more of the daughter isotope until you reach the point where you're basically trapping all of the daughter isotope inside the crystal. So this region in here is called the partial retention or partial annealing zone. You can maybe just think about it as partial retention right now. And of course, the name is kind of obvious, that it means you're retaining some of the daughter product that's produced, but not all. So down here, you're losing it. Up here, you're keeping it all. And in the gray zone, you're keeping some of the daughter product. Now, I think I more or less have already said this here. If you want to think about this for a second, I haven't really said anything about any specific thermochronometer yet, but if you want to have some idea of like what these temperatures would be, for some systems this could be like 100 degrees C where you're losing all the daughter product, and then maybe 60 degrees C where you're trapping it all. So some of these systems are would be relatively shallow in the Earth's sort of the depth in the Earth at which you would record the capture of the daughter isotope. Others can be much higher temperatures, so you can go to 500 or 600 degrees, getting even close to like the temperature of crystallization for some of the minerals. So because we have this kind of gray zone, both sort of figuratively and literally here, one thing that's been done is that there was a work done in the 1970s already where they just said, let's put this kind of red dashed line here in the middle to just give us a sort of approximation of when the system transitions from being open to closed. So just to divide it in half and to say at the point where we start trapping 50% of the daughter isotope, we're going to refer to that as the closure temperature, or the temperature at which the system then starts trapping all of the daughter isotope. And the useful thing about this is that if you have this temperature in mind at which the system closes, now you can start to relate your ages to some temperature in the Earth. And as I mentioned before, then you can start to figure out where that temperature is and then calculate things like how long it took your mineral to come from that temperature up to the surface. And yeah.
So do they have empirical data on when the annealing zone starts and ends?
Yeah. So a lot of this comes from doing experiments with like basically heating up minerals in a furnace and looking at the system behavior and how it changes. And the unfortunate thing is you then have to extrapolate to the rates of cooling in the Earth, because oftentimes like those experiments will happen at much faster rates of cooling than would happen in nature. So like if rocks are being, even if some place where you have like very high mountains and big powerful rivers and things like that, rocks are still only coming up to the surface at a rate of maybe 2 or 3 kilometers every million years. And when you translate that to a cooling rate, it means like the cooling is like 10 degrees per, it could be maybe 10 to 20 or 30 degrees per million years. So obviously, we're not going to run those experiments in the lab at those cooling rates. So there's a kind of big extrapolation that has to happen, but essentially this information would come from doing experiments on real crystals, heating them up, and then looking at the kind of temperature at which the release of helium, for instance, stops, because then you sort of know that you've gotten above the temperature where everything should be kind of moving out of the crystal. So anyway, this closure temperature idea is something that will come up in today's exercise, and well, in both this week and next week, and the final report as well. So it's an important thing just to kind of have in mind as the approximation of when the system closes, the kind of rough temperature when we think we start trapping things. And it's a simplification of nature, but it's not too bad. This closure temperature will be different for different minerals and different for different daughter isotopes. So for helium or argon, the temperature will be different depending on which mineral you're looking at. And yeah. So here's a little bit of kind of information to kind of maybe put some of the things we've been talking about in perspective. This is a plot of different cooling rates. So you can see here like geological cooling rates of 1 to 10, maybe 100 degrees C per million years. So as far as people go, that's really slow. But 100 degrees C per million years cooling rate for geological system is quite fast if it's the result of kind of rock being eroded and brought to the Earth's surface. And then this is a plot of the effective closure temperature for a bunch of different mineral thermochronometers. Don't worry too much about like what all these different letters mean. Some of them are referring to apatite as the host mineral with, for instance, helium as the daughter isotope. So that's the top one, AHE, is apatite with helium. Then the bottom one down here is hornblende with argon as the daughter isotope. What you see is that as the cooling rate changes, so does this closure temperature. So like very slow cooling rates of like 0.1 to 1 degrees C per million years for the hornblende system, you're about 500 degrees for this closure temperature. As the cooling rate goes up, you go almost 100 degrees higher for a faster cooling rate. And that's a little bit complicated to explain. If you want, we can maybe talk about it after we're finished with the slides here, because it takes a moment to go through why that is. But you'll see this as well in the exercise this week when you play around with it, that the closure temperature will change for different rates of cooling. The important thing for, like, if you have one of these mineral systems where you measure an age, is to think about this closure temperature changing, because that will change the depth at which you think your mineral might have come from. All right, so let's talk a little bit here about what causes cooling. It's not really something I don't think that people think of too often here, because the landscape is not particularly rugged and rates of erosion are generally pretty slow in shields. But the question that we would want to address normally is, what does our cooling age, or what does this age related to time since the rock was at a closure temperature, what does it actually mean? And we can talk about that a little bit here. So the general picture here is like the kind of geophysicist's rendering of what mountains look like if you take a cross-section through the Earth. So this is supposed to be the Earth's crust, so maybe something like 40 or 50 kilometers thick. And these are supposed to be mountains, of course, not drawn to scale. And as you know, we have rivers that are eroding the landscape. We've got glaciers in a lot of places that are also removing rock at the Earth's surface and transporting it away. And then hill slope processes like we've seen before with the hill slope diffusion or landslides or whatever. Essentially what's happening all the time is we're eroding rock from the Earth's surface. It gets into a river system, for instance, and then gets transported away to someplace where it's deposited. And as you remove this rock, you are continually exposing rock from below to the surface. And over long periods of time, this means that the rocks that are at some depth are gradually moving up toward the Earth's surface. So you get a picture that looks something like this. You've got rock uplift, where relative to the Earth's surface, because of erosion, rock is moving upward. And this is something that is often addressed with thermochronology because we can relate things like this rate of rock uplift to ages that you measure for a given thermochronometer. Just to add a couple things to the picture here, if you walk along the Earth's surface here and collected a rock sample here at this green dot, the idea is that that rock sample would have traveled up from depth to the Earth's surface. And, well, I don't have the picture here, but essentially what this age you might get for the rock at the surface would reflect would be its slow exhumation toward the surface as a result of different erosional processes. So could be river erosion, could be landsliding, and more than likely it's a combination of those things. You can also exhume rocks, though, by tectonic processes. So in places where you have extensional tectonics, you can directly expose rock to the Earth's surface just by fault movement. So if you've got a sort of normal fault like this, and the two sides are pulling apart, as the footwall is exposed to the surface, these rocks here were previously below the Earth's surface and are now exposed as a result of fault movement. And so you don't necessarily need erosion to get rock to the surface, and in some cases you can then relate things like ages of these rocks to the rates of fault slip on a fault like the one that's kind of shown in cartoon form here. There's other things that can happen too. I mean, if you happen to be working in a place where there's some kind of magmatism, so intrusions or volcanic activity, sometimes your thermochronometer ages will be related to that. You can imagine if you had a rock sitting at the surface and there's like a lava flow that flows over the top of it, that's going to heat the rock up quite a bit, and you may lose all of your daughter product from that, and so your age would then be dating the age of that lava flow potentially. And of course, you can also reheat samples, like if you're in a sedimentary basin, the rocks can get buried and then later brought to the surface. So there's more complicated scenarios that we can deal with as well, but they're not so much a concern for us. But what we can focus on now, maybe until the end of this little lecture, is a little bit about how we can calculate these thermochronometer ages. And we can start with just the general age equation for any kind of radioisotopic system. So any mineral system that's related to decay of some parent isotope to a daughter isotope follows a general equation like this, where the age or the time that you would measure for that sample is related to the inverse, so 1 over the decay constant, which is related to the half-life, times the natural log of 1 plus the amount of daughter isotope divided by the amount of parent isotope. So this is concentration of daughter isotope divided by concentration of parent isotope. So this would work for, basically any geochronometer. As I mentioned, though, the kind of exception we have with thermochronology is that the daughter isotope doesn't always get trapped in the crystal. It can be lost, and so we have a little bit more complicated picture here. And for that, we need to deal with diffusion, because essentially that's the main way in which this daughter isotope is being lost, is by diffusion of the isotope within the parent crystal. So for most of these systems, like for helium is a noble gas, argon's a noble gas, and both of them, when they're inside a crystal, don't go into the crystal structure, but they're basically trapped in the space in between the atoms that make up the crystal structure. So if we have normal atoms in some crystal, and here I've just drawn it as a very kind of cartoonish crystal of regularly spaced grid of points. In some cases, we'll substitute in a parent isotope like uranium or thorium in place of something that should be in the crystal normally. So if this is supposed to be an apatite crystal, I don't remember what the formula for apatite is offhand. But in some places, it's possible to substitute in something big where there should be a normal atom in the apatite crystal structure. When we've got decay of one of the parent isotopes, you produce, in this case, the daughter isotope, which is green, and you can see it's not going into the crystal structure. It's just sitting in between the elements and the atoms that make up that crystal structure. What that means, because it's not in the structure of the crystal, is that it will basically diffuse within the crystal because it's basically a foreign atom. It doesn't really want to be trapped inside the crystal, but it's not going into a structure in the crystal, so it's going to undergo diffusion. And the diffusion equation, as you might remember, looks something like this. So in this case, looking at the case of diffusion of some atom within a solid crystal. So we've got some differential term here about the number of the daughter isotope changing per time being related to D, which is a function of temperature. This big D here is the diffusion coefficient, and it's a function of temperature. So diffusion's faster at high temperature than low temperature. And then the kind of gradient in concentration of the daughter isotope. It's actually the kind of curvature, so the derivative of the gradient, plus some term at which the daughter isotope is being produced. So this is our picture for diffusion, and this is a 1D picture, but it's good enough for us. So in terms of finding the solution for this or getting an idea of how this diffusivity varies, it's often solved in this form, where the kind of diffusion constant as a function of temperature is divided by A, which is the diffusion domain. It's often the size of the crystal, if you wanted to think about it that way. It's basically how big is the crystal, although for some systems it gets a little bit more complicated. And that's related to the kind of diffusion at infinite temperature, so that's what the D0 is. And then some terms here like the activation energy and temperature at which the mineral is being held. So that kind of determines how fast diffusion will occur. There's some activation energy that's needed to get diffusion started. Temperature will come in here, and then, of course, the kind of properties of the mineral in which diffusion is happening. And I guess maybe you've seen this kind of thing before, possibly. It's not really that uncommon if you've done any kind of course where you've had thermodynamics in there. This is a pretty common equation to have encountered, but if not, it's not such a bad thing to deal with. So in terms of this diffusion picture, we can sort of change the way in which we look at the kind of trapping of the daughter isotope inside the crystal to look something like this. So if we have a plot here of temperature going up versus time and some rock that's cooling down, what you see is as it's cooling, it follows a curve that looks like this. It's sort of an exponential shape because the diffusion process will change exponentially as a function of temperature. And so the top plot shows temperature cooling down for the crystal. The bottom one is showing the ratio between the daughter product and the parent isotope. So for instance, here you see at high temperatures, there's basically no daughter product. And as you go to low temperatures, so over here, the daughter product to parent ratio is a kind of straight line. And the closure temperature we were talking about before is basically in between these two behaviors. It's not really so important that you remember all of these different names, but maybe you'll encounter them somewhere else. Excuse me. TO in this case is the temperature at which the system is open, so no retention of the daughter product. TB is called blocking temperature, so that means everything is trapped in the crystal. And then the closure temperature, as I said before, is just halfway between those two. That's not really critical for what we're doing. Yeah. It's the daughter to parent isotope ratio. Yeah, so it should go to a straight line when the system is in equilibrium, assuming that you've not run out of parent isotope. But yeah, I mean, you could think about it this way, that each time you've got a decay of the parent isotope, you kind of take, well, depending on how much you produce by decay, you take away one from the parent isotope and you add one to the daughter. And so it should give you a straight line that's like a 1-to-1, or should have a slope of 1, I think, if I'm not mistaken. If the number of daughter isotopes you produce by parent decay is 1, then I think it should give you a straight line with a slope of 1. So yeah, I mentioned before this closure temperature thing, and well, I won't belabor it too much, but we're going to deal with this equation for Dodson's method, which comes from this paper in the 70s about how to calculate this closure temperature, how to approximate what the closure temperature is. And it relies on making a sort of simplification of how the diffusion process works that allows us to figure out when this closure temperature should be reached. So if we assume that when you go into this partial retention zone, so when you start to accumulate the daughter product, that the temperature is going to be kind of directly related to the inverse of time, or in other words, that the cooling is kind of constant, you can then find the approximate value of this closure temperature by doing this sort of simplification here. The math doesn't really matter too much, and you can read through the description in the exercise for this week as well to get a sense of how it works. But there's a little bit of math involved, and you can end up with this thing where you have this kind of time constant called tau that relates to temperature, the cooling rate, gas constant, and the activation energy for whatever diffusion system you're considering. And then that tau goes into this equation here for the closure temperature, which again basically has a lot of the same terms. There's a geometry factor in here that you have to think about if you've got a sheet mineral versus something that's more like a sphere or a cylinder. This geometry factor will change how much of the daughter isotope is trapped in the crystal. But yeah, again, activation energy is something related to the diffusion, gas constant, this shape factor, the kind of thing for tau up here, and then otherwise this diffusion, diffusivity at infinite temperature, and then the size of the crystal. So yeah, and we can solve this thing relatively sort of in a relatively straightforward way just by iterating, and I think it's kind of described here what you can do. So if you want to solve this Dodson's equation to find a closure temperature, basically you have some constants like activation energy and other things that you define. You have some initial guess value for tau, because to calculate the closure temperature, you need to have some value for tau. It really doesn't matter what you put, because if you solve this in an iterative way, just like calculate the value of closure temperature and then update your value of tau with the new closure temperature estimate and just kind of loop over that a few times, it very quickly converges to a solution. Kind of doesn't matter too much what you guess at first. But all you do is kind of go back and forth, where the T here that you put into this equation for tau is the closure temperature that you calculate here, and the value of tau you calculate goes into your closure temperature calculation here. So it's like each one depends on the other, and if you have a little loop, you could go over it 5 or 10 times, and you'll see that the value of closure temperature will stop changing pretty quickly. And then you've got your estimated value. So that's kind of described here. You don't really need to worry about this, because I'm not going to make you do that part. You'll use this equation, but I've kind of already set that up for you, because there's a lot of places where you can get sort of into trouble. In spite of this being kind of a simple thing, there's you can screw a couple things up and then like be stuck trying to figure out why your code doesn't work for a long time. So I don't really want that. But yeah, if you do it, you can plot things like this closure temperature for the apatite system, where uranium decays to helium, and you see for different cooling rates how that closure temperature varies and that it's higher like you would expect for faster rates of cooling. Yeah, so a couple more things here. Let me see. I think this is kind of our last main slide. So the main point of using this Dodson's method is just to allow us to figure out what the closure temperature is and then try to relate that to some kind of geological process. And there's a few different ways in which you can do that. We're going to deal with one of them in the exercise this week, where we use a thermal model to determine how temperature varies with depth. And then we'll use this Dodson's equation to calculate what a closure temperature is. And since we know exactly with the thermal model how temperature varies with depth, we can then very easily figure out like what the rate of exhumation would be for some mineral sitting at the Earth's surface. So yeah, as quantitative geologists, we can do better. Well, that's essentially the plug for the exercise for this week. So here we are, end of the introductory stuff, and I guess that wasn't really particularly interactive kind of lecture. And I'm sort of, based on faces, thinking maybe it's not a bad idea to ask you guys these questions for once. So if we talk about this basic idea of thermochronology, what's the kind of general concept? Yeah, right. So it's the kind of idea that, in contrast to geochronology, where we've got a parent isotope decaying to a daughter and we trap everything, we have to consider here temperature. And the system closes at some point, and then after that, then we have a meaningful age. But exactly as you say, we have to think about the temperature in order to figure out what that age actually means. So then for the closure temperature, what's the kind of, if you had to give a definition of a closure temperature, what might you say for that? So it's the kind of estimate of when the system closes in terms of temperature. There's still some potential to lose a little bit of daughter product below this effective closure temperature, but it's the kind of point where we start trapping at least half the daughter isotope. And of course, in nature, things aren't as simple as this, but I don't want to be too nasty to you in the first exposure to thermochronology and make you deal with the kind of reality of what we think goes on. But yeah, so I think that's the kind of general idea. And if the picture isn't crystal clear right now, that's not necessarily a problem. I say that for a couple reasons. One is that there is this set of slides about low temperature thermochronology. I'm not going to go through them, as I said, but they'll be on the course page. And essentially here, these slides go through some different thermochronometer systems and how they work. So if you want to know kind of more about, like, at the mineral scale, what's going on, we talk about in these lecture slides things like the decay chain of uranium to produce alpha particles. So in the case of this uranium, thorium, helium dating method, there are several ways in which alpha particles, which is the same thing as a helium nucleus, get produced, and the decay of uranium-238 produces some, 235 produces some, thorium-232 produces some, and even samarium-147 produces a bit of alpha particles. It's often not considered because it's like a pretty small contributor, but in some minerals, samarium actually makes a difference. Anyway, you can read about that and some other dating methods in the slides that will be up on the course page. And in addition, there are these slides about quantifying erosion with thermochronology. And essentially what I tried to go through a little bit here is some terminology about rock exhumation and erosion, in a bit more detail, and then some ideas about heat transfer related to erosion. So it's actually quite useful with respect to this week's exercise to at least look through these slides. I don't really like giving lectures for like 2 hours straight, so that's why I'm not going through them all now, because I think your ability to absorb material after 2 hours of me talking is going to go kind of to zero. So that's not so good. But you can go here and kind of take a look at some different work that's been done looking at rates of erosion and thermochronometry, and yeah, there's more stuff to be seen there. And then last, I think what I'm going to do here now is I will go through these slides. This is a kind of introduction to the exercise for this week, as well as the exercise for next week, and a little bit about the final project kind of thing that relates very closely to both of these exercises. So we'll go over this stuff, and then I'll get you the exercise and things like that. Everything should be ready to go. There's a bit of a technical problem with the course page that I need to quickly sort out. That was a kind of surprise this morning because I thought I was all set to go, but I think I have a fix for that, and the course page will be updated with a link to the exercise. I can put it in Slack as well, so you can get started. But let's go here first. And for the exercise 6 and 7, we're going to deal with some data from the Himalaya of Bhutan. And this is just kind of a nice picture, not my picture. I've not been to this part of the Himalaya, but very nice place, and one of these places where thermochronology has been applied quite widely to understand rates of tectonic and erosional processes in the last maybe 5 to 10 million years. And essentially, kind of how did this landscape develop is one of the questions there. So the Bhutan Himalaya over here in the east. So you can see the kind of inset map here with India as a reference point, and this would be kind of the southern margin of the Tibetan Plateau. Bhutan is in the eastern part of the Himalaya, and we're dealing with data that comes out of a paper published in 2014. And we're only taking about half the data. We're just dealing with the western, what's called the western transect in this paper. You can see there's a bunch of different colored dots here, and each one of those dots is an age from a thermochronometer system that was measured. So there's a few different ones here, and again, you might want to look at the lecture slides to kind of know what the difference between this apatite, uranium, thorium, helium, and apatite fission track is. But you can see basically here all the different colored dots. I can't remember in all, maybe there's something like 80 ages that were measured, and we're going to deal with looking at those data a little bit with the code that we'll use for the exercise this week and next. In fact, this week we won't even deal with the data. We're just kind of getting things set up for next week. But anyway, here's where it comes from, western part of Bhutan. And I won't say maybe too much about the details of the tectonics here. It's an active part of the Himalaya, and so there's faults that are active, and it's also a place that's, at least in the southern part, fairly wet climate. So the ages here are, in this case, now plotted kind of on a transect showing from like south to north, so from 26.5 degrees to 28.5 degrees latitude. And then ages are plotted along the vertical axis here. And you can see for the different colored dots that there's different ages for the different thermochronometers. It looks like I left the little legend off of here, but I believe that the blue colored ones would be the uranium, thorium, helium, and apatite, and pink is probably uranium, thorium, helium, and zircon, but it doesn't really matter so much for now. The point is that these ages are going to be related to the rates of tectonic activity, so the faults that are active in this area, as well as erosion. And if you look at this data, I mean, you can perhaps already see that like there's quite a lot of variability in ages, and it's not necessarily something you can just look at and say, yep, I can see how fast this area is eroding. So the interpretation's a bit challenging, and that's why we're going to use a simple numerical model to kind of help out with that. Now, in the lecture slides, I kind of went over this idea that you have rock exhumation that's related to erosion. So when you have rivers eroding, glaciers eroding, it's removing rock from the surface and exposing the rock beneath it. And then there's a definition here for like exhumation, because that's essentially what we're going to estimate is how fast is that rock coming to the Earth's surface. So if we have a thermochronometer age, what does that age tell us in terms of how fast the rocks are moving up from depth to the Earth's surface? I don't know. I just put this picture in here because I think normally I feel like people are kind of brain dead already at this stage. So this is just a nice picture. It doesn't have anything to do with our exercise for today. It's just a pretty place. Okay, so time to kind of power up a little bit mentally. And the simplest way that we could kind of calculate one of these exhumation rates would be that we can assume the geothermal gradient is constant. In other words, we can assume the change in temperature with depth is a constant thing. So oftentimes people will say like, oh, the geothermal gradient is 20 degrees C per kilometer. So the question here is, if we have a closure temperature, for instance, of 75 degrees C, and we've got an age of 12.3 million years, how would you take this information and come up with an exhumation rate? Yeah. So if we assume, for instance, that the surface temperature is 0, then we could say, okay, well, we've got 75 degrees C, and if we take that and divide by the kind of geothermal gradient of 20 degrees C per kilometer, we should get out of that 3.75 kilometers as the depth at which we would hit 75 degrees C if we just started tunneling down from the surface. So once we have this depth, we know that our age is going to be something in millions of years, I guess 12.3 in this case. So our exhumation rate, which we call E dot, would just be the 3.75 divided by 12.3 MA. You can see kilometers per million years here, so that's looking good. And if you do that, does anybody have a calculator or want to just type that into their phone or Wolfram Alpha or whatever you want to use to? Yeah, right? So about 0.3. Yeah. So yeah, thanks. And that's, well, essentially what we do here. So it's, in principle, this is not necessarily something that's hard to do. If we look at kind of places where we have a bit of uncertainty, okay, we've got some uncertainty in the age, so 12.3 plus or minus some stuff. But the biggest kind of place where we can get into trouble here is this 20 degrees C per kilometer, because it basically, if you look at the shape of a geothermal, or the shape of a geotherm, it's not often a straight line. It's pretty close to a straight line here, but even here where there's almost no significant erosion, the geotherm is not straight, and that's in part because of past climate effects, that it's a bit out of equilibrium from the past ice age still. So in the shallow surface, the geotherm is not behaving the way we might expect it to. But calculating this exhumation rate is pretty straightforward. But yeah, using a geothermal gradient that's constant is a bad idea. And there's a lot of different ways in which you can demonstrate that. So what we're going to do instead of using a constant geothermal gradient to come up with our temperature is we'll use a thermal model. And so we'll calculate things like this, where we can just say, okay, we have the temperature as a function of depth across the whole thickness of the lithosphere in this case. So this is coming from an equation here, which is just the case for a steady state with a constant rate of advection or constant rate of vertical uplift. And you can see, I guess, pretty clearly that's not a straight line. So yeah, that can introduce a bit of uncertainty in your age calculation if you assume a straight line. Now, for us, the kind of tricky thing that we need to deal with is if we have the temperature field, that's going to be the first part of what you'll calculate in the exercise for today. And I can tell you, you're not going to use an equation that's this simple, but you also don't have to code it yourself. If you want to, you can, but it's a little bit nastier. But if we have a way of calculating how the temperature varies with depth, the really kind of more useful step instead of this constant geothermal gradient would be to actually calculate what is the cooling history of the rock. So as it goes from depth up to the surface, if we know the rate that the rock is being advected, so basically how fast it's moving up toward the Earth's surface, we can actually, using the thermal model, calculate what the temperature is at different depths as the rock moves up toward the surface. So you'll do that in the exercise for today, and it's in the description of the exercise a bit as well. But the idea is fairly simple, I think. And if we know the surface, like let's say that the rock is sitting at the surface today, we'll say z equals 0 as a kind of easy elevation to assume. And we know the advection velocity in the thermal model. We can figure out what the cooling history is, and I guess I was meaning to ask you the question of how, but I've kind of given that away. And that is that we can figure out what the past depths were by using the kind of going back in time, essentially, and saying, let's go back every 10,000 years and say, how deep was this rock and what was its temperature at that depth? And each time that you move up toward the surface, you're just taking that velocity you're moving at and multiplying by some time increment to move up by some small amount. So if we look at our geotherm that we had before, back at some time t1, we have the temperature here at this depth and time. At some later time, we have this temperature T2, which is at a different depth and a different time, obviously. Temperature T3, T4, and so on until you reach the surface. Here we have basically a history of the temperature of this rock as it moved from somewhere deep up to the surface. And we can use this then as our way of figuring out what our thermochronometer age means, because this is showing us basically how temperature has changed through time. If we know the closure temperature, we can figure out what depth we were at when we passed through the closure temperature, and then we know the rate of exhumation from that. So yeah, does this kind of make sense or not really? Yeah, kind of. Okay, you'll get to play with it a little bit this week in the exercise. So I'm erring on the side at the moment of like just trying to getting you started on the exercise rather than going through this in more detail. But we can come back if there's questions about this once you start on the exercise. I'm happy to come back to the slides and explain some of these things a bit further. So the way that we're going to work in the exercise for this week and next is you can do calculate some thermal solution. So basically, we put in the values to this temperature calculation, do that, come up with the temperature history based on that thermal solution and the velocity at which rock is moving up toward the surface, use that thermal history to calculate a closure temperature, and then record the time at which the rock cools below that closure temperature, which is basically the age we would have for that mineral, and then compare that to the ages that are measured from the western part of the Himalaya in Bhutan. And essentially, you could just then do that over and over again until you get a good agreement between the measured ages that were observed in the Himalaya of Bhutan and our prediction from the numerical model. And that's actually what you'll do in exercise 7, is that kind of repeat step. Okay. That's that. And are there any questions about this kind of exercise 6 and 7 concept? So I'd like to stop talking rather somewhat soon, but I'm going to show one thing. As I mentioned, the course page is not up to date yet, and I think I have a fix for that, but I have not been able to test it out yet. But I guess, have you been here and looked at this final report thing on the course page at all? Has anybody looked at that? Yeah? So just to give you some idea, if you haven't looked at it, for exercises 6 and 7, you're going to produce a bunch of plots, and then the final kind of thing in the course is to write a paper that's like roughly 6 to 8 pages, including the text and figures, and relates to what you've plotted in those 2 exercises, and includes also a little bit of information about like the geological history of the place where we're working in the Himalaya in Bhutan. The structure looks something like this. So there should be some kind of short abstract that basically summarizes what you found in the exercises and how it relates to the area that we're studying with in terms of erosion and tectonics and things like that. And then it's pretty much a standard layout for like a scientific journal article. So there's an introduction section where basically all you want to do is kind of tell the reader, I guess me in this case, but what you've done and why, like what it means, kind of why it's significant. And then, give a little bit of background about the kind of the topic in general. And then there's a section on geological background. So there's like, I think I've got links to at least 5 or 6 articles that you can kind of look over to get some.
Given to one of them,
There's no access to one of them?
Yeah.
Okay, all right. I can take a look at that. But the geological background should give you some, or should give the reader rather, some information about the kind of tectonic history, the climate, or sort of erosional history of this area. And you can get that mostly from the papers that I've listed, although you're certainly welcome to look up some of your own articles if you're interested. The methods basically describes what you do in exercise 6 and 7. So that's kind of a quick summary of like what was done. And then the results are some of the plots that you would produce, and maybe a little bit of text describing what those plots are. And then you can have a couple paragraphs of discussion at the end where you talk about like what you found and what it means in terms of the tectonics and erosion story that you would have perhaps discussed a little bit in the background and introduction section. So I've got a couple things it looks like I should update here in terms of exercise numbers, but after that, then just a short conclusion, a list of any references, and then as an appendix, if you're writing this like in Word, I ask you to kind of copy and paste in some of your code, but I'm not sure actually. That's what I did previously. I don't know how that's going to work with the Jupyter Notebook. Maybe I'll have you just like print the Jupyter Notebook as a PDF or something like that, just as a way to kind of see like what your code looked like. So that's the final project idea. There's also a kind of grading thing here, so you can get an idea of like what each section should say and how many points each section is worth. So I think that's a sort of useful thing to look through. And then there's the articles, and I guess at least one of them is not, the link doesn't work. So is it just that there's no access to it?
Yeah.
Okay. All right, yeah, it looks like we don't have access to this one. Okay, so I can find another way to link that. I didn't want to have links directly to the PDFs on the course page, but maybe I can post a link to the PDF on Slack. so that you can get that first article. That's quite a useful one for a kind of overview of thermochronology. Any questions about the final report thing? I'll probably come back to this again next week just as a reminder of what to do, and I think maybe we'll try also to make a template if you want to do this. If you want to write the final report in Jupyter, like in a Jupyter notebook, I think that would be kind of a useful thing to do actually. And so I can maybe make a template of the Jupyter notebook that you could use then, like check it out, and then you could even like maybe I'll just make a separate GitHub Classroom assignment so that you can also return it in GitHub Classroom like the other exercises. I haven't come up with a clever way to figure out how long a Jupyter notebook should be, because like obviously in Word you get page count and things like that, and I don't know of an equivalent for Jupyter notebook, but I can think about that a little bit for next week. But yeah, any questions about this at this stage?
Yes, sorry. About the background that is given, so it's from exercise 6 and 7 or so.
This geological background,
yeah, so
that should mainly be from the articles that like provided for this. Well, here for the scientific articles for the paper. It really should be a little bit about like. There's a couple articles in there that are like reviews of the tectonic history of the Himalaya, and it should be kind of something about like, yeah, which faults have been active and kind of how the study region may have evolved in terms of tectonics and erosion. So
You have to choose a specific art, just like read about some of them.
yeah, and if you want to find some others of your own choosing, that's fine as well. These are here because like I think they're probably the easiest place to get started, and I think you're asked to refer to at least 5 or 6 articles. So essentially you could just look at these 6 and be done. But if you're curious, of course, you're welcome to look around for other things as well. And there has been more work that's been done in this part of the Himalaya using thermochronology since 2014. So you could find some more recent papers if you want. But I think, so you're asked here to include at least 5 primary sources, and there's 6 articles. So I suspect that the majority of people will not go beyond those 6, but of course, you're more than welcome to do so. Other questions? All right, so then let's have a quick look here at the exercise for this week. And I will try to emphasize the quick part of this look. So for exercise number 6, the GitHub Classroom link and all that stuff's working, but the course page is not updated yet, so I'll put the link in Slack in a moment. But basically, we're going to do 2 things in this week's exercise. One, we're going to calculate temperature using this lovely equation here. You might realize now why I said you don't need to worry about coding this one up, because it's not necessarily difficult, but there's just a lot of parentheses, and people spend a lot of time like fixing mismatched parentheses and not actually doing anything useful. So anyway, this equation allows us to calculate temperature not only as a function of the advection velocity, but also as a function of time. And when you put time into this equation, it automatically gets nasty. This is like probably the simpler, or one of the simpler versions of the heat transfer equation in 1 dimension with including time. So this is already in the exercise for this week as a function. You don't need to do anything. But the important point is to realize that temperature will be changing as a function of time in this exercise. It starts out with a straight line of constant geothermal gradient, and it's going to evolve over time as you run the numerical model. It's this comes from some book from the 1950s.
What's the year?
It's the complementary error function, which is defined down here. I don't know if I have a kind of nice explanation for what that equation means, but yeah, I mean, this is the kind of mathematical definition of the complementary error function here. So again, fortunately, there is a Python module that has a complementary error function in it, so we don't have to worry about coding this thing up. You can just use the version that's available. So yeah, the first step is, as I mentioned, to calculate temperature using this complementary error function. If you're interested, we didn't go through the notes in detail, but there's something about solving the advection diffusion equation. This is essentially what the 1D heat transfer equation is when you have advection and heat conduction. So if you go to lesson 4, you can find the notes on solving that equation there if you want to know a little bit about how things work out to looking something like this. So I don't deal with this particular version of the equation, but you can find something about that in the earlier lesson notes. But problem number 1, basically, you're just going to run through and produce a handful of plots of different temperature values. And there's a few cells that you can run at the start, just like standard kind of setting things up. We're using from this SciPy module this complementary error function, so we just bring that one in. That's the only thing that's really different than normal. And then here's the 1D heat transfer equation. As you can see, like, it's not that bad, but there's just a lot of parentheses. And then there's the code that we're going to use, which is called age predict, and it's defined as a function, and it's pretty long. I think it's maybe a couple hundred lines long function. So again, you don't have to modify much of this. I kind of want to just give you like a working starter code here. You'll have to make a couple minor changes, but they're not really bad things, I don't think. At least in years past, people haven't really had too much trouble with it. The thing I would ask you to do is just to look through here. I mean, a lot of these lines are things like defining constants. So these are like diffusion parameters for helium and apatite. And there's some stuff like converting units. So like when it comes down to it, the number of lines where it's actually doing something kind of complicated, there's not that many. But before you just like run this cell and get started, it's good to just kind of read through and just look at the headings for some of the comments and try to like see what different sections are doing. And if you have questions, then you can ask myself or ask Lotta, and we can help. So anyway, you're going to run this cell, and that's going to define a function called age predict, and then you can use that to do some of the plotting. And it should work just by itself, like right from the start. So for the very first part, you're basically going to produce a plot that looks like this. And as I said, it should work without any need to modify things. What I'm going to have you do in the first part is like add some axis labels, add a title. That stuff is already actually in here. So it's literally just put in the text for the axis labels and title. And then have you add the advection velocity, so the rate of advection using the plt.text function. So you'll have to look in the code to find where that value is defined, and then just use plt.text to make it show up on the plot someplace. After that, then you just kind of play around a little bit with some of the variables that control the temperature in the thermal model. So change how fast the rate of advection is, change how long the model runs in terms of the geological time that it's running for, change the initial gradient in temperature, and then yeah, add some extra plotting stuff, and then there's some questions. This, I think, should be kind of straightforward once you get a sort of chance to look over the code. After that, then we go to predicting thermochronometer ages, and again, this is done for you. So this Dodson stuff is you can see the two pieces here, so calculating tau and then calculating the closure temperature. That's already done down here in a function called Dodson. It's also not that bad. There's a whole bunch of stuff you have to pass into it, but in terms of what it does, like the tau equation basically just is this, and it's really not that complicated. And the Tc is the closure temperature, and that's Tc here. So again, just take a look at the function. You don't have to do anything for this section other than just run it so that it's defined and able to be used. And then after that, like the previous section, you just enable some different flags to get the code to calculate different thermochronometer ages. And you'll produce a few more plots and answer a couple questions, and that's pretty much it for exercise number 6. So in terms of the amount of coding you have to do, it's not that much. Maybe if we had 3 or 4 weeks, I'd have you code more of this, but spread over 2 weeks, I think it's mostly that you just try to spend a little bit of time to look through the code and see if you can understand what it's doing. And if you have questions, I would say it would be good to ask us so we can help explain how the code works or if there's anything that's unclear about how things are working. So that's that's exercise 6. Are there any questions about that? I guess I could have made this a bit bigger. But yeah, any questions about exercise 6? So what I'll do is I'll put the link in Slack for the exercise and then see if I can set to work on getting the course page to update. And then everything should be all set on the course page if I can just get it to update. And if you have questions, Mota and I will be here for your assistance. And yeah, so I'll get this link posted to Slack here, and you guys can get started.